Okay, so the Chem 1, the June 14 paper, excuse me, so from the most recent exam, besides obviously the one that's going to happen this year, which isn't the most recent, it's in the future, I guess. But anyway, the most recent exam is available now publicly, so I'm going to run through that start to finish, give you some sort of hints on sort of where to score the marks, run through as per sort of what you would need to write on each one of the questions, where you get the marks, as I say, and hopefully that will give you some sort of points to those of you who are working through papers, and particularly those of you who have want to see how the paper obviously worked, this most recent one. So, normal starting thing, nice little logo they use now, it's nice, well done AQA. Hour and 15 minutes, we've got 70 marks in total there, so not too bad compared to the 100 marks in Chem 2. So I'm hoping, this is an hour and 15 minutes, I'm hoping to do this in about 45 minutes, but we'll see. So, question 1a, table 1 shows some data about fundamental particles in an atom. We've got masses, real proper masses in grams of protons, neutrons and electrons. An atom of hydrogen can be represented as H1. Use data from table 1 to calculate the mass of this hydrogen atom. This is a question which isn't actually sort of as bad as it may seem, because you've got these sort of horrible looking numbers there. It's actually okay. But the way to tackle this is to think, what does hydrogen contain? Well, hydrogen contains a proton and an electron. It does not contain a neutron. Therefore, we're going to do this value here, add it to this value here, and we're going to get 1.6734 times 10 to the minus 24 grams. You can convert it to kilograms if you really want, but I wouldn't. It's an extra step to get wrong. Obviously, the easiest way to do this would be, excluding the times 10 to 24, just do 1.6725, add 0.0009, and then stick the times 10 to 24 on the end afterwards. So hopefully a nice easy start to the paper. People get tricked out because they forget to add the electron in as well. They just do it as a proton. Which of the following is a fundamental particle that would not be deflected by an electric field? Well, we know electric fields linking into mass spectrometry. Charged particles are deflected. This has no charge, therefore B is going to be our neutron, which is going to be non-deflected. So, naturally occurring sample of the element boron has a relative atomic mass of 10.8. In this sample, boron exists as two isotopes, boron 10 and boron 11. Calculate the percentage abundance of boron 10 in this naturally occurring sample of boron. Now, looking at the numbers here, there are a few ways of sort of doing this. I find it easy. I find it very hard to explain how to do this, and just sort of one of those you sort of get that feeling of. And if you think about it as, best way to explain this. So you know you've got boron 10 and you've got boron 11, and we know really that having a relative atomic mass of 10.8 means that we have majority of it must be made of this, in order to, obviously, when we average the amounts of each of these, we get to 10.8. The answer is 20% of boron 10, and you can kind of see that if we know that between 10 and 11 we have 1, and we have sort of 0.8. Let's not explain that very well at all. But between here we have a value of 1, and we could say 5 0.2s if you like. So 4 of those 0.2s must be from here, and one of those 0.2s must be from here, which is a value of 20%. Alternatively, there's another way of doing it. I've taken this directly from the mark scheme, which is another way to sort of go about this, which is sort of more algebraic, which is potentially a little bit more difficult depending on how you feel about your maths. Is to use the examples that you'd use similarly to the mass spectrometer, in that we would look at our isotopic mass multiplied by the abundance over total abundance of both of them, so in this case x plus y equaling our relative atomic mass. So once more, so this is our boron 10 multiplied by its abundance, boron 11 multiplied by its abundance over the total abundance x plus y. When you basically sort this all out, what you end up with is a ratio of 10 to 11. You end up with a ratio of basically 0.2 to 0.8. Again, the idea being here that percentage wise really here is 20%. A bit of a difficult one to explain. I don't think I've done a massively good job of that one, so hopefully you can sort of see what I'm saying there. it is manageable, but it is a bit of a pain, really. I don't think it's the nicest question in the world. The answer's more obvious than the explanation. If you get the answer, you get both marks here, so don't stress about that. A state in terms of fundamental particles, while the isotopes B10 and B11 have similar chemical reactions, same outer shell electrons, I should say same number of outer shell electrons, or you could say same electron configuration. Either of those would work. Table 2, suggest a value for the third ionization energy of boron. I like these questions, but a lot of people don't. So thinking behind this, you might say, well, how can I predict a value? I don't know what's going to happen. And it's all about sort of using the trend that you can see there. So for boron, if we think about the old school, the fact that it's in group 3, the old school sort of way of representing it is that it has 3 outer electrons. Therefore, we know that this is coming from the outer shell, this is coming from the outer shell, and this is also going to come from the outer shell. So these are the outer electrons. This is now the fact that we've now moved down to another shell, which is why it then jumps up so high. The easiest way to do this is look at the difference between these two and then add it on to get to here. So the difference between those two is going to be 1621. Add it onto here and you're going to get 4041. And that's going to be an absolutely fine answer to have. You're going to have no problems with that at all. They're quite generous in the mark scheme, what they let you have. No issue there. So, write the process that occurs when the second ionization energy of boron is measured. So we're looking to create the 2+ ion here because it's the second. We're creating the 2+. So we start with boron, always gaseous, and we make the 2+ ion, again gaseous, and we have an electron there, which is fine. You can do minus electron on this side, but it's just better to have the plus electron over there. It's just sort of by convention. Explain why the second ionization energy of boron is higher than the first. The first one, you're taking it away from an atom. The second one, electron being removed from positive ion, which therefore requires more energy. Electron being removed is close to the nucleus, various other answers as well. That one I think is the most straightforward one to get. So we're 8 marks in, and let's hit up question 2. So, when heated, iron 3 nitrate, MR of 241.8 is converted into iron 3 oxide, nitrogen dioxide, and oxygen. Here's the equation of that occurring here. So a 2.16 gram sample of iron 3 nitrate, this chap, was completely converted into the product shown. Calculate the amount in moles of iron 3 nitrate in the 2.16 gram sample. So we're given its MR here. I mean, they couldn't have made it any easier. So moles mass over MR is going to be mass 2.16 divided by 241.8, and that is going to give us a delightful value of, and I'll do it in standard form, 893 times 10 to the minus 3. Note here, very key thing, give your answer to 3 significant figures. Don't start ruining it because you'll just completely throw those marks away. If it's not to 3 significant figures, you will lose the mark, okay? Very, very important. Calculate the amount in moles of oxygen gas produced in this reaction. So oxygen gas here, they've chosen a nasty sort of a ratio there. How I would do that, we know we have 8.93 moles of this, making 3 moles of that. I would say 8.93 times 10 to the minus 3 divided by 4, and then I would times that by 3. That's my thing. My dividing by 4 is getting me to 1 mole, multiplying by 3 is taking me to my 3, which is going to give me a value of 0.00670, or again standard formalised. You could do that. 2 marks there, nice. Straight away I'm seeing R, so I'm thinking PV nRT. So I'm going to write that down before I do anything else. Calculate the volume in meters cubed of nitrogen dioxide gas at 293 degrees Celsius and 100 kilopascals produced from 2.16 grams of iron nitrate. The gas constant is 8.31. So let's rearrange this first of all. We're trying to find the volume. So let's do volume equals nRT over P. Now, N, what is N? Well, we've got to use this one here. We've got to work out what's going on. So we know that we have 8.93 moles of iron nitrate, and we know that we're trying to find this specifically, so we're looking to convert that out there, and so 8.93. Let's do this. So first of all, let's work out our moles then. Moles of NO2, it's going to be 8.93 times 10 to the minus 3 multiplied by 3, and just in case you're curious there, my ratio of this is 1 to 3, so I'm multiplying by this by my molar value by 3 to give me the moles of nitrogen dioxide that was produced. This comes out to 3 significant figures. This comes out to 0. We'll do it. It's 0.0269. No, it's not. 79. That's going to feed directly into here. 0.02679. R, scroll up a little bit. R is given to me as 8.31. T is given to me as Celsius here. Don't get that confused. It's 293 add 273, which comes to a total of 566. All divided by my pressure P, which I've got to convert. So 100 kilopascals is going to be 100,000 pascals. Bit of calculation. Boom. V is therefore going to be 0.00126 meters cubed. Note that it's asking me to convert it into meters cubed, or sorry, calculate it in meters cubed, which is fine. That's the usual unit for volume in the PV and RT. So not too bad to go through there. Obviously, make all your steps clear. So this a few times to the kids I teach. You've got to, in this one here, when you write this out first of all, PV equals NR2, okay? Once you've done that, show that you have, don't instantly get to this step, show that you've rearranged it to put V as a subject with nRT over P, and then put your numbers in, okay? You can get a mark often just for that one, and if you do miss out on the answer, you want to be able to go back and get the other mark, so important. And again, I've made it very clear that I've got my moles of my NO2 there with a calculation, so do make it very, very clear what you're doing in calculations. That's 4 marks, ridiculous. So iron nitrate, what kind of reaction does it undergo? Well, I've got one thing breaking down straight away, thermal decomposition, or just a decomposition. We'll call it thermal decomposition there. Suggest why the iron 3 oxide is pure. Assume a complete reaction. This one's quite a nice question. It's one of those suggest. Suggest means that it's not necessarily an answer that you definitively will know, but you've got to try and work it out. So this is broken down. I'm producing a solid, 2 gases. Well, when I produce it, my gas is going to escape. So other products are gases, and they will escape. Nice easy mark there. So question 2 down. We're up to question 3 this time. A bit of metals now. Nickel is a metal with a high melting point. State the block in the periodic table that contains nickel. Well, nickel is from that middle block, so it's from a D block. 1 nice mark. Explain in terms of its structure and bonding why nickel has a higher melting point. Nice standard sort of metal question. So we have positive metal ions strongly attracted to negative delocalized electrons. I think that's actually going to be the 2 marks. The idea that we've got the positive ions and we've got the negative electrons is going to be 1, and the strong attraction between them being the actual metallic bond. Draw a label diagram showing the arrangement of particles in a crystal of nickel in your answer. You should include at least 6 particles of each type. Excellent. So I'm always a bit loath to sort of draw it without the electrons. I quite like drawing electrons as well. You could squeeze some electrons in there. You often don't get the marks for it, but I just think, why not? Electrons look cool. Key things: charge in each one of the ions, and obviously make sure we have at least 6 particles. I wouldn't start drawing 100, just wasting your time. Fill up the page, circles everywhere. Charges are very, very important. The actual charge doesn't normally matter. We could have gone nickel 2 plus. It's not really a problem, but 2 nice marks for that. Explain why nickel is ductile. They even give you what it means, stretching like wires. Well, again, layers of ions can slide over one another or over each other. Standard sort of answer there. It's very easy, sort of a very generic metallic bonding sort of question, that one. Okay, going a little bit more out there now. Nickel forms the compound nickel 2 chloride NiCl2. Give the full electron configuration of the Ni2 plus ion. This is an important one. You've got to make sure you don't get tricked out by this. Start, fine, 1s2, 2s2, 2p6, 3s2, and then we're around 3p6. And remember that whilst it would be normally 3d8, 4s2, these are the electrons being lost. Okay, so whilst these add first, they are removed last. Sorry, they are added first and they are removed first as well. So it's going to be 3d8. Don't worry about the 4s0. Okay, down here, balance the following equation. Just because there are lines here doesn't mean we need numbers in every single one. Okay, just put it there to not really help you massively. So I want to balance it. Well, my nickels, they're balanced. I've got some H's there, and I've got H's here, so I've got 12 here. So I'm initially going to put 12 here to balance up my hydrogens alone. I've now got 12 chlorines. This side I've got 2 and another 2 there. Also, no, I've got 12, 14. So I'm going to balance this up. Another 12 there, which gives me, leaving this alone for now, gives me 2 and, oh dearie me, what am I doing? Absolute schoolboy this. I know what I meant to do. I want 12 in total, so I need to 6 because it's doubled it, sorry. So I've now got 12, add the 2, 14, so my chlorines are balanced, my hydrogens are balanced. Oxygens, not massively balanced at this point. I'm trying to work out what I've got. I've got 6 there. I've got now 6 there. I've got 12, 2 there, so 6 here, and that's going to be my lot. So 6, 6, and 12. Nothing in front of there. Nothing in front of there. Identify one substance that could react with both gaseous products. So gases, this one and this one. Straight away, acidic gases. What's going to react with it? You've got a choice. Choose something alkali. I'd probably go NaOH. Probably a straight one. Calcium carbonate, something like that. Something that is basic or alkali. Nice. So questions 3 down. Question 4. Ammonia gas readily condenses to form liquid when cooled. Name the strongest attractive force between 2 ammonia molecules. Straight away, we've got hydrogen present. We've got hydrogen bonding. Love it. Draw a diagram to show how 2 ammonia molecules interact with each other in the liquid phase. Include all partial charges and all lone pairs of your electrons in your diagram. Right, so straight away, I'm going to draw one ammonia, and then I'm going to arrange it because I know that my next ammonia I want to be drawn in a very particular way. So, lone pair. You could draw this either way. You could draw it like that, or you could draw it like that, the little balloon thing. I don't mind. It's up to you. This is my delta negative region, delta positive. I would put all the partial charges as it says. And then this is my bond between there. That's going to score me 3 marks. I've shown my lone pairs, I've shown my partial charges, and I've shown the idea of a bond being formed between the lone pair and the hydrogen. Really nice, easy 3 marks. Look at this one. So now we've got a dative covalent question. I know that because it's, well, I know that because I know that the nitrogen here reacting with the boron, 2 electrons there, and also I've got this arrow shown which denotes the dative covalent bonding. So boom, straight across the nitrogen using both its electrons. So nitrogen uses its lone pair to form covalent bond with the boron atom. Boom. Or the nitrogen donates its lone pair, whatever you want to say. The idea being that both of those electrons, the lone pair, comes from the nitrogen to the boron. So it gives value of some elements. I just put that there because they're quite fancy. There's no real use at all. There we go. Give the meaning of the term electronegativity. So, still on question 4. It is the standard definition here: the power of an atom to withdraw. I'd perhaps use the word attract actually. Withdraw electrons in a covalent bond, and that's going to get you 2 marks. That standard sort of definition of the term electronegativity there. Boom. Power of an atom to withdraw electrons in a covalent bond. Must be in a covalent bond, and it's the power of the atom to withdraw electrons, not an electron. It draws them both, remember. So something like hydrogen chloride would find them much more over this way. Not just one of them, both of them, due to the electronegativity of the chlorine. Suggest the formula of an ionic compound that is formed with a chemical combination of 2 different elements from table 3. Straight away, ionic, I'd go for metal and non-metal. Metal, non-metal, boom, LiF. There are other options. You can have lithium oxide. You would need to write that as Li2O though. LiH, metal hydride. I don't come across those very often. I would stick with LiF, to be honest. Nice, easy one. So it's the formula of the compound that has the least polar bond and is formed by a chemical combination of 2 elements from table 3. Least polar means the closest electronegativity, so it's going to be this one and this one. Standard BH3 as a result. So we're looking at boron having those 3 electrons in its outer shell, therefore 3 bonds are going to be made. It doesn't complete it, it's a bit of a weird one like that, but that doesn't matter. 3 bonds being made to our hydrogen. They're similar to nitrogen. 1 more mark, and that's our 9 marks out of the way now. We're on to question 5. Some oil-fired heaters use paraffin as a fuel. One of the compounds in paraffin is the straight chain alkane dodecane. To give the name of the substance from which paraffin is obtained, state the name of the process used to obtain paraffin from this substance. Right, so alkanes, where do we get them from? Crude oil. How do we separate them? Fractional distillation. I've already spied this next question. Combustion. Incomplete combustion, dodecane, gaseous products only. So we know that in this reaction we're not going to produce carbon, we're going to produce carbon monoxide. I'm not going to put in state symbols on this one. We know we're going to produce water because we always do. We're reacting with oxygen, even though it's incomplete, still oxygen. I'm going to move that slightly because I'm going to have to balance this, I would guess. Particularly because dodecane is a big old hearty C12H26. So straight away, balance the carbons first. Always do this in the same way. Carbons balanced, 12 there, boom. Depends if you've got an alcohol, because we haven't got alcohol, it's very, very easy. So we've got 26 hydrogens there, means we've got to have a 13 here, and then we've got to balance up our oxygens, 12 here, 13 here, gives me 25. This needs to be 12 and a half to balance that up, and that's 1 mark for all that effort. Oxides of nitrogen are also produced during the combustion of paraffin in air. Explain how these oxides of nitrogen are produced. Well, first of all, nitrogen reacts with oxygen. Fairly easy. Now you've got to remember, you've got to bear in mind that in the air that you're currently breathing, I hope you're breathing, nitrogen and oxygen are there and they're not reacting. So what's causing it? Well, it's the combustion here. We've got high temperature, so it's nitrogen reacting with oxygen at higher temperatures. You'd easily get the 1 mark just for saying about nitrogen reacts with oxygen. It's this other one here which people tend to struggle on slightly more. Write an equation to show how nitrogen monoxide in the air is converted into nitrogen dioxide. Right, so we've got our nitrogen dioxide. Got nitrogen oxide. Yeah, monoxide. Nitrogen dioxide. I've got a feeling this might be one of those you just need to learn. Either way, O2 there. Balance it up. Boom. 4. Finished. Nitric acid HNO3 contributes to acidity in rainwater. Produce an equation to show how nitrogen dioxide reacts with oxygen and water to form nitric acid. So, nitrogen dioxide reacts with oxygen and water to form nitric acid. nitrogen oxide, oxygen, and water. Yeah, just got to balance it up now. So, where are we going to go? Where are we going to go? Where are we going to go? Let's first of all, we're going to go here. It's one of these where you're just going to kind of have to sort of play around with it. Yeah, it looks alright. Yep, stick with that. Yep. There's sometimes when it comes to balancing equations, you just got to sort of start somewhere. This is one of those annoying ones where it's not. I find it very difficult to know where to start. You've just got to start somewhere and see where you get. Use pencil would be my advice. Don't use pen. Obviously, do it in pen at the end. You need to write in black ink, but you know, go for it pencil style. So, give the general formula of the homologous series that contains dodecane. Okay, alkane. I think we even told it back at the start, aren't we? Even tells you it's an alkane. So, homologous formula, bam, CnH2n plus 2. 1 mark. Yeah. Down. 5D part 2. Write an equation for the cracking of the long question of one molecule dodecane into equal amounts of two different molecules, each containing the same number of carbon atoms. Right, so the equation. So, dodecane is being split, and it was C12H26. So, we know we've got to have a C6, and we've got to have a C6. One's going to be an alkane, so that's going to be C6H14. The other's going to be C6H12. It's an alkene. Add them up. That works fine. The alkane is this guy here. What's my empirical formula? That's my simplest ratio, whole number ratio. In this case, C3H7 divided by 2. The catalyst of this is going to be a zeolite catalyst for the cracking reaction. 5D, part 3. Explain why the melting point of dodecane is higher than the melting point of the... Right, okay, so dodecane is bigger. Because it's bigger, therefore, stronger van der Waals. Boom, intermolecular forces, size increases. The bigger they are, stronger the intermolecular force, particularly when, well, van der Waals case. The question 5 is still going. How is this happening? UPAC name. Don't be tricked out with this. They've done this sneaky little job of putting methyl groups on the end. Look for the longest carbon chain. So here, 1, 2, 3, 4, 5, 6. I draw a line like that. Really make it clear what's going on here. That's our longest chain. What have we got attached? Using the lowest numbers possible. So we've got 2 here, 2 here, 2 here. So it's going to be, that's our first carbon, second, third, fourth, fifth, sixth. So carbon 1, 2, 3, 4, 5, 6. We're not going to start from there. It's going to give us the highest numbers. We'll start here. So we've got 2, 2, 3, 3, 4, 4. Annoying. Make sure you don't just put 2, 3, 4 either. It's got to be 2. It's got to name every single group that's attached. It's 6, so it's hexa. You have the A there. Methyl and hexane, because it has that 6 carbon basic sort of structure there. What kind of structural isomerism is that showing? And dodecane chain straight away. Dodecane we know has that 12 carbon thing, hence the reason it's dodecane. This one's got 6. Excuse me. Hexane, therefore it's got to have chain isomerism. Dodecane can be converted into halododecanes. Use the formula of a substance that could be reacted with the dodecane to produce one chlorododecane and hydrogen chloride only. Should be able to sort of work this out. If it's chlorododecane, we've basically got, if this is my rest of my molecule, then we obviously want to put a chlorine here. We're going to produce HCl, so we're adding Cl2. Okay, that's one of those sort of thinking a bit more outside the box slightly on that one. But again, not too difficult really as far as questions go. So that was question 5, 16 marks, massive. We're on to question, or section B, question 6. Calcium phosphate reacts with aqueous nitric acid to produce phosphoric acid and calcium nitrate as shown in the equation, which is this one right here. Oh, nice. A bit of calculation. So, A 7.26 gram sample of calcium phosphate reacted completely when added to an excess of aqueous nitric acid to form 38 centimeters cubed of solution. Calculate the concentration in mole decimeter cubed of phosphoric acid in this solution. Right. So, look at what we're going to do for this one. So, calcium phosphate is reacting with nitric acid. Okay, first of all, let's look at the moles then that we've got. So we can calculate knowing the mass and working out the MR. We know that moles is mass over MR. I always tend to write out my equation first off. Makes me feel a little bit more comfy doing it. My MR here is going to be 310.3. I'm going to get a value there of 0.0234. And that's my value of moles now of that. So let's have a look here. We've gone over here, we've got a ratio of 1 to 2 because we are calculating the concentration of phosphoric acid. So this was the moles of Ca3PO4 This is the moles of H3PO4. That's going to be 0.0234 times 2, which is going to give us 0.0468 moles of, this is the phosphoric acid that we've got there, moles of. Okay, so what have we got? Okay, so we've got the concentration here, we've got a volume, 38 centimeters cubed, so concentration equals moles over volume, 0.0468 divided by 38, which we need to divide by 1000 or times by 10 to minus 3 to convert the centimeters cubed into decimeters cubed. Calculate that out and we get a value of 1.23 moles decimeter cubed. So quite a bit of work in that, but 5 marks, you know, it's a good reward for sort of the effort we've put in there. So calculate the percentage atom economy for the formation of calcium nitrate in this reaction. So there's calcium nitrate. What we're going to do is we're going to add up the total mass, if you like, which is basically the MR of each one, including multiples. And it's going to be this value divided by that. So it's basically the proportion of this that forms this. So in that case, skipping ahead to the various numbers, which obviously you will work out, 492.3 divided by 688.3 times 100. It's going to give us 71.5%. Quite a nice easy 2 marks on that one. That's ridiculous. Write an equation to show the reaction between calcium hydroxide and phosphoric acid to produce calcium phosphate in water. So we've got phosphoric acid given to us before, H3PO4, calcium hydroxide, CaOH2. We're going to produce calcium phosphate, so it's going to be CaPO4, Ca2 plus PO4 3 minus, so it's going to be Ca3 PO4 and of course water. Let's balance this up. So PO4, we've got 2 PO4 groups, one there. So let's double that. That gives us 2 PO4 groups, which is great. We've now got 6 hydrogens there. We've got 2 more there. That's 8. Is that right? Oh, hold on. Hold on. We can't do that. Yeah, we've got to balance our calcium. 3 calciums here. That's fairly important. That now gives us 6 hydrogens there, 2, 3, 6 more there, so we're going to need a 6 here to balance that up, and that is balanced. Nice. Oh, still going. calcium dihydrogen phosphate can be represented by the formula CaH2PO4X, where X is an integer. A 9.76 gram sample of calcium dihydrogen phosphate contained 0.17 grams of hydrogen, 2.59 of phosphorus, and 5.33 of oxygen. So, let's have a look here. Let's write all our elements out. That'd be my advice. Start with Ca, H, P, and O. Now we know 0.17 of hydrogen, 2.59 of phosphorus, 5.33 of oxygen. The difference there, the remainder, sorry, is going to be my calcium, which in this case is going to be 1.67. Now we calculate our moles of each one, so we do divide by 40.1, divide by 1, divide by 16. Phosphorus is 31. We're going to get various values here. We're going to get 0.042, we're going to get 0.17, we're going to get 0.084, we're going to get 0.333. So when we ratioify this one, we're going to find if we divide it by the smallest number, which in this case is that one, we're going to come up with a ratio of 1, 4, 2 to 8. Now, we know that calcium is on its own, which is great. We've got a ratio of 4 to 2 to 8. Well, that's double this, 2 to 1 to 4. So, X therefore must be 2, because that allows for us having the, so I just completely lost my train of thought there, having X being 2, whatever it was here, X being 2 would give us here H4P2O8, which is what we're getting there. So the empirical formula then would be, because it does ask you to write that as well, calculate the empirical formula and hence the value of X. Probably done it in a bit of a weird way around, but it'd be Ca, you could do it in two ways. You could do it as H4P2O8, or going from what they've done, the example, Ca H2PO42, and that's 4 nice little marks. So it's not too bad. Different, bit of a twist on the normal sort of empirical formula question, but I quite like it. 12 marks there. I think this is probably the final question now. Question 7. So thallium is in group 3 of the periodic table. Thallium reacts with halogens to form many compounds and ions. Draw the shape of the TlBr32- ion and the shape of the TlCl43- ion, including any lone pairs of electrons that influence the shape. So Tl3, group 3, straight away 3 electrons. So this is, we'll do the first one. We'll do TlBr32-, and then over here we'll do TlCO43-. So TlBr32-. Let's look at this. So Tl has 3 electrons in its outer shell. Okay, bromine each brings 3, so that gives us a total of 6. It's 2-, so we add 2, that gives us 8. 8 divided by 2 is going to be 4. That tells us we've got 4 pairs of electrons. 3 things are bound, therefore 3 of those pairs must be bonding pairs, the other one must be a lone pair. Therefore we're going to have our lone pair here. Looks like a ghost or an alien. Oh. Not required the shapes, I'm sorry, these things, but I like to do it anyway. I think it's sort of good practice. This one, same simple again. 3, add 4 this time is going to equal 7. Add 3 is 10. Divide by 2 is going to be 5. And again, that's 5 pairs. So 1 lone pair here, 4 bonding pairs. So Tl. Oh, what a weird, funny shape. Just stick them all in. It wants the value of the shape of this one. So the shape here is going to be just like ammonia. It's going to be a, scroll down slightly, trigonal pyramid. The bond angle there, if it was normal tetrahedral, would be 109.5. This constricts by 2.5 degrees. Therefore, bond. Oh no, it's frozen. Bond angle equals 107 degrees. Nice. Thallium-1 bromide TLBr is a crystalline solid. I'll just go back up there. See that once more. Melting point of 480 degrees. Just the type of bonding present in thallium-1 bromide. Suggests why the melting point is high. So we've got metal or non-metal. I would suggest ionic. Why has it got high melting point? Because we've got strong attraction between oppositely charged ions. Fairly easy for 3 marks, that. Oh, end of questions. Look at that. Oh. Write an equation to show the formation of thallium bromide from its elements. So we are told here thallium bromide is TLBr. So Br2 TL. In this one, you could double this up. Strictly speaking, if from unit 2, the enthalpy of formation, which isn't part of this, which is why you can do it, enthalpy of formation, you are forming 1 mole. So I would, out of sort of convention, halve this one, and that's going to give you 1 mark, and that is the paper done. Whew. I hope that's been of some help. I've gone through that reasonably quickly. Not sure how long that's taken me, but there we go. So I hope it's been of some help anyway. By all means, give me a shout if there's anything you want to ask or if there's any problems. But there you go. That was the June 2014 Chemistry 1 paper.